In this video, we're going to talk a little bit about how to wrangle data, how to prepare it, process it for the types of analysis we might be interested in down the road, but also about the Tidyverse, which is sort of a newish way or approach to working with data. I think most math and stats students, when they think of data, they think of it in a way that's compatible with the Tidyverse. But this isn't how database administrators or people who just do data analysis in general think about it, at least not when I was a kid. So we'll talk about the Tidyverse and how it can be implemented in R and how you can actually process data in a very neat way. One point to note, the Tidyverse is being updated constantly. And so the tutorial that I'm giving you now, which is based on a tutorial by Hadley Wickham and Garrett Rollman, might be outdated fairly soon. The ideas stay the same, the ideas behind data wrangling and the Tidyverse, but the actual specifics of how we can actually create tidy data sets in R, these might change. So you'll have to sort of keep up with the updates on a regular basis. Okay, so we start by loading in two packages, the Tidy R Package and the Dply R Package. You could also load those directly by just loading the Tidyverse package, but for now we'll load both of those packages. And we'll notice here that some of the functions have a name which is the same name as something you would find in the base package and stats package. So now certain things have changed. If you're going to be writing code that uses these functions, you need to make sure that you're using the definition according to TidyR and dplyr, not the one according to stats and base. It might not give you the results you want otherwise. We're going to work with 5 data sets. I have uploaded them in the data folder, so you'll have access to them there. If you don't have the data folder available to you, you could also upload them from the EDAWR library here. I'm not gonna load that for you, but you have to install that package first, obviously, and then you can load it and you'll have access to the other data sets. 5 data sets of interest, something called the storms data set. That's a built-in data set with R. You don't need to load any library for that. Cases, pollution, TB, they come with the EDAWR package. And then the cities data set, that's an artificial data set that I made. So this one I'll have to load it with the from the data folder. So let's take a look at the first of these data set, the storms data set. Alright, so what I'm looking at here is it's a tibble. It has a fair number of observations, about 10,000, a fair number of variables, about 13. It basically gives me information about storms. So the name of the storm, the year, the month, the day, the hour, and then its location. And well, there's actually a few more variables, and perhaps hard to read from the tibble as it is being displayed here. If we look at the structure of the data set, we'll get more details. So name, year, month, day, hour, latitude, longitude, the status that the storm had at that point, because these change potentially over time, the category, wind speed, pressure, and then 2 other variables called TS diameter and HU diameter. Fair enough. So these are the first data set. The second data set is the cases data set. So I'm going to load it from my data folder, but you could also load it directly from EDAWR. The problem here is that if I try to find my working directory, I find that I'm in the directory users and then I click Bully, which is my main folder in Mac, and that's not where my data folder is actually found. right? My folder is actually found in this location. So now there's a data folder here, and if I try to read the CSV, then it doesn't bulk at it. It says, yeah, okay, it makes sense. This is where the cases dataset was. So let's take a look at what the cases dataset looks like. It's a fairly simple dataset. It has 3 rows, 4 columns. You get information about a country, presumably France, Denmark, presumably perhaps, or perhaps Deutschland, I'm not sure, US, and then some variables, X 2001, X 2012, X 2013. So this is a little bit of troubleshooting that you have to do, and it's annoying because I haven't set my working directory to be where I'm actually working here. That's poor preparation on my part. I should really be working from some main working directory that is always the one I'm working from. That's not what I did here. There's also a pollution data set. Also very small, and it has 6 rows and only 3 columns, city, size, amount. And then we'll have a TB dataset. Now this TB dataset is bigger, so when we look at it, you'll notice for cases in pollution, I wasn't looking at the structure. I could actually just display the full dataset. It's because I happen to know that it's a fairly small dataset. The TB dataset is too big to just display in its entirety, so I'm going to look at the structure. Then I get it has 3,800 observations, 6 variables, some information about countries, about the year, about sex, child, adult, and elderly, whether they and the number of TB cases. Okay, so that's the these are the data sets with which we will work. All right, let's talk about the pipeline operator. Now, the version of the pipeline operator that I'm going to be using is this one, and that's an operator that gets loaded in when you load in the Tidyr and the Dply R package, something we did up front. There's been an update recently, so it's going to be using vertical lines instead of this weird percentage arrow percentage. Principles stay the same, and for the time being, that's an acceptable way to run this, but eventually you'll have to keep up with what Hadley Wickham and the people that are thinking is the best way to go for the pipeline operator. So R is a functional language. Functional language means that in general, if you want to run a bit of code, you might see something that looks like this. So this is an example that Hadley Wickham had shown in one of his papers. So there's a lot of parentheses, a lot of nested parentheses. It makes code somewhat difficult to read. Here you're creating a data set called hourly delay, and in order to get to it, there's a number of steps you have to take. I mean, you can figure out what's happening here. It's not too difficult. We're going to filter some summarized data set, which will have been grouped by some other filtered, and then we're starting to lose track of what's happening, right? I mean, you can take the time to figure out what is meant here. And in fact, I would well, encourage you to try to do so. But the pipeline operator is used to basically remove the need to nest your function calls. What you will do instead with the pipeline operator is you're going to pass data from one function to the next. Now this code won't run here because I don't have a data set. Of course, all of this is commented out, but I'm going to show you the version of this code which is written using the pipeline operator rather than the somewhat convoluted nested function bit here. Okay? So what are we seeing? It's pretty easy to read what's happening here because you just read it aloud and you can figure out what the block of code is meant to do. So this is what's happening here. Take the flight data set, filter it so that you remove all the observations that had a missing value for depth delay. You're going to group the resulting observations by hours within day. You're going to compute the mean delay within these groups, and you're only going to be displaying or keeping those hours within days for which you had more than 10 flights. The pipeline rules are pretty simple. This is the piece of code that you use, the percentage, arrow percentage, to pass the thing on the left to the first argument of the function. So the filter function is a true function. It exists. It typically requires you to have a data set and then, well, something that you want to filter on the data set. So the pipeline operator tells you whatever was immediately to the left gets passed to this function into the first argument. There are ways to actually pass arguments or objects into a second, third, fourth argument of a function. I'm not going to talk about this here, but there's a way for you to do that if you need to do that as well. But that's basically a shortcut notation to write, in this case, filter, flights, comma, what the rest of the thing you're trying to do. And the nice thing about this is a 5-line block of code as opposed to this nested monster. And you can see how this might even be very, very useful if you wanted to build a more complicated series of instructions here. We notice a few things. I'm going to go back here for a second. Look at the setup here for the cases data set. We have a country on a row, and each of the columns correspond to a different measurement of the same quantity, except it's being measured at different times. Compare that to the pollution data set, where on each row you have exactly one measurement of whatever it is that is being measured here. The pollution, I guess the largest amount of pollution and the smallest amount of pollution that is being connected. There's a structural difference between these two data sets. The second one, the pollution data set, is in a format that we call the tidy format. Each row corresponds to exactly one measurement. The original data set, that would be in a long or wide data set format, depending on the situation. Okay, so more often than not, we think it's preferable to put things in a tidy format. Now, you could imagine a setup where there would be a second column here of measurements, or a third or fourth or what have you. The difference being that these measurements might measure something else altogether. Like this one here measures some sort of pollution quantity. And if you had a second column here that was measuring temperature, or that was measuring rainfall, or something which isn't the same quantity being measured, you would still have a data set in a tidy format. But if each of the measurements, each of the columns represents the same type of measurement just taken at different times, then you're not in a tidy format. The package Tidyr has two functions that can help you reshape tables to a tidy format if they're not already in a tidy format. There's a gather function and a spread function. The gather function, it requires a data frame that you're going to be reshaping and a key column against which you will be reshaping. A value column which contains the new variable of interest, and then the indices of the columns that need to be collapsed. Let me show you an actual example that's going to make more sense here. So we are going to look again at the cases data set. Just as a reminder, it was basically a 3x4 array. What do we think this function here would do? Well, it's going to gather the cases according to the year, and it's going to give me the actual value for these years, and I want you to do this for columns 2 to 4. So basically, it's going to look at each of these columns, and it's going to call them a year, and the value that is in these entries will be called n, and by doing so, by telling you that the information that needs to be reshaped is in columns 2 to 4, then we are going to get something that looks like this. The years have been corralled, the measurements have been corralled, and we've called them year and N. So now this is in tidy format. Each row represents a different observation, and the variables that we have, the year and the whatever the measurement and number of cases is, they show up in one column, not 2 columns or 3 columns. So we've added the year as a variable, is what we've done here, so that now each measurement shows up in one column. Now spread would be doing the opposite of what gather just did here. So for spread, we're going to work with the pollution data set. Let me remind you what the pollution data set was. It is already in tidy format. We're going to put it into a wide format if you want. And so what we're going to have now is, New York, London, Beijing, 2 variables, large and small, and then the measurements associated with them. So then we would expect it will be to sort of transform this 6 by 3 array into a 3 by 3 array. And it does so by basically the way you expect it to do so. It needs a data frame to reshape, it needs a key column, and it needs values so that you know what you do with it. So here it's going to spread the pollution size and amount, and what we're going to get is something that looks like this. For each city we have a large measurement and a small measurement. So spread and gather are smart enough to know what it is that they're supposed to do. There's other wrangling functions that exist, like for instance the separate function and the unite function. I'm not going to run them here. But what do you think these would do? It'd be worth looking at. Trying to get a sense of what these functions do. And then there's the Dply R package. I'll show you what some of the things that it does. It is very useful when you need to transform tabular data. The Dply R package isn't like officially part of the Tidyr package, but they're both in the Tidyverse family. The Tidyverse family is a family of packages that are all compatible with one another. So the Dply R package is compatible with the pipeline operator. So the functions that exist in the Dply R package that are quite popular, like select, filter, mutate, summarize, group by, these functions can then be used together with the pipeline operator to create, well, what you would expect to see them do. So let's look at a little example. We're going to look back to the storms data set. I remind you we had about 10,000 observations. So what we're going to do here is create a new storms.2 data set. It's going to select amongst the storms the name and the pressure variable. Now you need to have loaded the Dply R package for this to work. Select is a function from the Dply R package. Let's actually look a bit at what this would do here. I'm just going to call the first few rows. And sure enough, what we've done is we have a data set that still has the full amount of observations. I only see 6 here because I'm only looking at the head of the data set, but it only has the name and the pressure variable for the data set. We could also create a new data set where we're going to try to keep everything but the name. So minus here would say I'm not keeping that one. If I go to the head of that, well, yeah, there's a bunch of them and I've lost the name here. It's not here anymore. We could also do initial selection. So I'm going to select from the storms data set all the variables between lat and pressure. So I should be losing the first variables here. Let's see what happens. Yeah, I'm only keeping the things between lat and pressure. It's quite a useful function, select. So it's basically helping you pick the variables you want, and then you can probably pick them by name, the name of the variable, rather than finding the exact index that corresponds to what it is that you want to do. And then you don't have to carry the annoying $sign notation that R sometimes uses, at least base R. You can filter. Now we've talked about filter when I showed you that first example originally with the flights data set. So what do we expect to see for storms 5? It is going to filter the storms data set, and it's going to keep only those observations for which the wind measurement was greater than 40. Right? Now, I'm not going to show you all of them, but remember how many observations we had originally. We had about 10,000. Now, once I've filtered how many observations I'm expecting to see, well, I've lost a fair number of observations here. Right? About half of them, a little bit less than half of them are gone now. And the storm 6, what would we be expecting this to do? It's going to filter the storms data set. Please only keep those measurements or observations for which the wind measurement is greater than 40 and for which the name is in this collection of names. It's either Amy, Alberto, Alexis, or Allison. So if we run this and we compute the number of rows, like we would expect that to be smaller as well, right? Because we have, you know, all the storm measurements where the wind speed is greater than 40, but only those that are in these 4 names. And well, sure enough, there's 123 of them as opposed to the 5,738. Mutate is another pretty useful function to use. What mutate does is it creates new variables for you. So I'm going to mutate here the original storms data set. I'm going to create a quotient, and the quotient would be the variable that I obtain when I divide the wind by the pressure. Now I got to make sure that pressure is never 0 in the data set for this to make sense. Otherwise, I'm going to get an NA. If you're okay with getting an NA, you can leave it as is. But you know, be aware that when you do mutate, there might be some issues with the domain of definition of your new variable. While I'm at it, I'll look at the storms 8, where I still mutate the storms data set. I still create a quotient, which is wind divided by pressure. And I'm going to create a new variable inverse, which is 1 divided by the quotient which I've just created here. So it's smart enough to be able to use variables that you're creating within the mutate calls to create yet another variable, which would be new. Let's run both of those. And now if I look at the head of my variables, storms 8 for instance, well, I'm having a hard time seeing it here because it's a tibble, and tibbles don't display nicely, but look at the number of variables. It used to be 13 and now I have 15. If I look at the structure of storms 8, yeah, I've created a quotient variable and an inverse variable. Now to show you how they are compatible, these dplyr functions, with the pipeline operator, let me show you here what would happen, say, to a pollution data set if I'm trying to summarize some of the variables. So typically summarize is a function that would require you to specify what the data set is, the pollution data set here, but we can write it in the pipeline format as follows. Pollution will be passed to the summarize function. What we're going to do with the summarize function is to get a median for the amount variable and a variance for the amount variable as well. And so the way this is created here, I'm not assigning the result of this computation to a data set, so I would expect R to just display the result. And it does. For the full pollution data set, here's the median of the amount variable, and here's the variance of the amount variable. Now, I can do a little bit more. Let me show you now the following bit. Same sort of structure. Instead of summarizing the median and the variance, I'm going to summarize the mean and the sum and the number of observations. Take a minute here to notice that the variable, or the function n, that counts how many observations you have, it does not take an argument. It has to be left empty. I don't know why. That's just the way summarize works. And so what we get for this one, same sort of idea. We know there's 6 observations, the mean was 42, and the sum was 252. Okay, so this is the summarize function from dplyr, and you see how you can also use the pipeline operator to make things happen. Let's go back to the storms data set for a second. I'm going to show you a function called arrange, which does some nice things with like sorting of the variables. Like the base R is not great for sorting in general, but arrange will do something nice for you. So storms 9, what it would do is it would sort the storms data set in increasing order of wind speed. Storms 10 will be assigned to the result of this call. We arrange the data set storms so that it's actually ordered with decreasing or descending wind value. And then you can do like multiple sort of sorts where we're going to sort on wind by descending year, by month, by day, right? So you might have something that ends up looking like this. So let's see if we can even get a nice sense of this here. If I do a head for storms 9, I should see, should I see that the observations are arranged or ordered according to the wind value. The problem is we won't really see it here because I have a Tibble display. So let's see what happens if we try to stick it to only the wind value. We're not seeing enough to really be sure. Let's look at the first 100 of these values. And yes, sure enough, we're seeing that the observations are being given or displayed in order of increasing wind values. A few other things that we can do, like I want to show you, as I said, the ability to use the pipeline operator. So this storms call here is basically the same call that we used when we created the storms 2 data set. We were selecting from the storms data set only the name variable and the pressure variable, and we had assigned it to storms.2. Here we're just going to do the same call. We're going to pass the storms data set to the select function so that we only keep the name and the pressure. We're not assigning it to anything, so we're going to see a display, but sure enough we're only seeing like the names and the pressure here, showing you at least that these calls are compatible with the pipeline operator. Same thing with the filter bit. Filtering the storms data set so that you only keep those observations that had wind speed of greater than 40. It's going to display it because we're not putting it anywhere, and it's in the Tibble format, and there's too many variables to see everything. If we dig in a little bit, we would see that we've only kept the observations where the wind value was greater than 40. And the next example we had done after doing this without using the pipeline operator was to filter on a number of things, right? Well, you can do so here. I'm going to show you an example where we keep only the name and the pressure for those observations and storms where the wind speed was greater than 40. And so what's going to happen here, something that looks like this. Now, it might be hard to tell because we don't have the wind value anymore, but these aren't necessarily going to be the same as this. Originally we had 10,000 observations, roughly speaking. For this one, we only have 5,738 observations. We're going to use the TB data set here, and we're going to show you a little bit of a, even more complex construction. So let's try to guess what this would do just by looking at the code. Okay, so it is going to take the TB data set, and we're going to group that data set by year and country, and then we're going to do a summary of cases. How many cases do we have in each year, in each country, in the TB data set? That's really what it's going to get from us. And the sum is going to add up child cases, adult cases, elderly cases. This na.rm equals true. If you remember from one of the basics of our videos, it's saying that if we have an NA in one of these years' countries, if there's a country in a year for which there wasn't any adult TB, for instance, we want the sum to be 0, not to be NA. So this allows us to remove, if you want, the NAs from the equation. Well, let's see what we would get out of this. And sure enough, that is what we get. We get country and year and then total number of cases, as opposed to the separate number of cases, child, adult, and elderly. Nice way to explain how group by works, country and year, cases. Now, if you removed the year bit of that here, what would you expect to see? We're only grouping by country, so we're saying that there's no real difference in the year. We're joining all the years together, and what we would expect to see then would just be a total number of cases over the history of the data set for each country. I'll show you another example of how you can use Dply R functionality together with the pipeline operator. What are we expecting to see here? We feed the storms data set to the mutate function. So we're going to create a quotient variable which takes the wind, divides it by the pressure for each storm at each measurement of each storm, and then we're only going to keep the name in the quotient. So what we would expect then to see is a bunch of quotient measurements corresponding to each of the times at which the measurements were taken for the storms. We're only keeping this the name of the storm in the actual quotient. Now what about this bit of code? What will we expect it to do? So it's starting to be a little bit more complex, but I'm hoping that you can see that even though the blocks are more complex, like the only thing that's complex about them is the number of commands that we're stringing together. But in and of themselves, it's pretty easy to get them to do what we want them to. There's no real difficulty here. Let's see. One issue that we have for this one is that my window might be a bit too small. Let me change the size of my window here so we see the code a little bit more. What would we be expecting this to do? So it passes the storms data set to the group by function. So here we're going to group them by name. Remember, for each storm name we had a number of measurements. We're saying now we want to report on this by the storm itself. So I'm going to try to find the maximum year for it. Some storms lasted, from one year to the next. If a storm starts on December 31st, a good chance it's going to move on to January 1st, in which case we would like to, have 1 year for it. We'll pick the maximum. The mean wind speed, presumably, is you give me your report on the mean wind measurement or wind spin measurement we had for the storm. And if there's one for which there's any times when we didn't measure the speed, if we have NAs, we don't want that to sort of like break the mean function, which is why we use NARM equals true. We do the same thing with the pressure, with the TS diameter, and with the HU diameter. I don't know what these things are, but let's look at it. And then we'll arrange it by year and by name afterwards. So we should be seeing a data set with a name, a year, mean wind, mean pressure, mean TS diameter, mean HU diameter, and only one of these measurements for each name. So let's look at it. Yeah, name, year, mean wind, mean pressure, mean TS diameter, mean HU diameter. So in many instances, TS diameter and HU diameter were not being measured. At least they weren't measured early on in the process. Now let's say we only wanted to see the tail end of that. Basically, this is what we would expect to do. We've created a data set. Now just show me the tail of that data set. And yes, then we're seeing the measurements that show up at the bottom of the data set, the 2015 measurements. And then we were measuring the TS diameter and the HU diameter, in which case, we don't have NANs anymore. We have real things. Let me give you a few more examples. The TB data set again. So we're going to group by country and year. We're going to summarize cases by counting the number of cases, child, adult, elderly. And once that's done, we are actually going to do the number of cases overall. So what should we expect to see here? We were grouping by country and year. So let me just remove this little chunk here. So we've done this one before, grouping by country and year and summarizing the number of cases. So when we run this, we have year by year for each country of the number of cases. We had done this before, and I showed you what happened if you removed the year bit. Now I'm going to show you can get the same thing by saying, like, this data set that we have here, do a summary of the cases. Add up the cases overall. And then what you would get at the end of the day is a country by country setup. And if you did it one more time, what would you expect to see? Well, you've actually removed one layer of the grouping. So that first summarize of the cases gives you a year by country total. The second summarize basically adds up everything within the country, so it removes this second variable in the group by function. And the third one basically says, well, just add it up for all of the countries. You would get exactly the same result if you did the following bit here. We don't group by anything, just summarize the cases by adding everything here. Notice the display is not the same. You did not create a table here. The last example we're going to work with is trying to turn the cities data set into a tidy format. If you look at cities as a data set, I get, okay, so there's 37 observations, 3 variables. We have a factor variable, large, medium, presumably small as well. So it's going to identify the type of the city that we have, and the population in 99 and the population in 2019. So these are the numbers here. For the sake of it, we're going to add a column that basically identifies the city. So now let me improve the readability by changing the column names as well. So I've added a 1 to 37 index, and I'm going to give them new names. So now let's take a look at this. Okay, city category 1999, 2019. It is not in a tidy format because if I look at it as an actual data set, I can see that there's a measurement here, the population, which is the same type of measurement over 2 different columns. So what would we expect to have to do in order to sort of turn that into a tidy format? We're going to use the gather function, which we've talked about before. So we're going to create a tidy data set. It's going to gather the cities using the year. So the year is going to be the new variable that I create, and the value that is going to populate this new variable will be the population. I only care about the 3rd and the 4th column in my data set. And sure enough now, I only have 1 column, which is a measurement. There's a lot of stuff you can do with the Tidyverse, with the pipeline operator. It helps you manipulate data. We're not talking about analysis here, but a lot of analytical packages are also compatible with the pipeline operator, in particular the ggplot visualization package, which I think of as an analytical package, is compatible with the pipeline operator. And that allows you to create nifty visualizations without having to worry too much about nested function calls.